This is NEAF Talks.
And now, ladies and gentlemen, the hardest working MC in the cosmos, Vincent Coulihan.
Thank you all, and welcome back for our next presentation. She's currently an associate professor of research in planetary science at Brown University and previously worked at NASA's Jet Propulsion Laboratory. Her research interests include impact cratering, modern-day geological processes on other planets, and the geology and exploration of Europa. She has participated in science and operations on many planetary missions and instruments, including Europa Clipper and NASA's InSight mission to Mars. Her talk today is on the Europa Clipper. It is the first mission designed to conduct a detailed study of Jupiter's moon, Europa. There's scientific evidence that the ingredients for life can and may exist already on Europa. Please welcome Ingrid Dauber.
Live at NASA's Kennedy Space Center for NASA's Europa Clipper mission, a nearly 2 billion mile, 5.5-year journey to Jupiter's icy ocean moon.
And liftoff. Liftoff, the Falcon Heavy with Europa Clipper, unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon, Europa.
Side booster separation confirmed.
Fairing is separated, and those will be recovered by SpaceX's own recovery ship, Go Cosmos.
This is a big moment for the program, for NASA, APL, and JPL. Let's watch.
Europa Clipper, separation confirmed.
And there you go. NASA's Europa Clipper probe, embarking on a long-awaited mission to study Jupiter's icy moon, Europa. And what a sight.
Now they wait for acquisition of signal.
And I believe we have it. There it is. Confirmation of signal from the spacecraft Europa Clipper.
So we are on our way to Europa. This launch occurred last October at Kennedy Space Center. I decided to start my talk with this compilation video of the launch because it seems like an apt beginning to the talk. It's the beginning of the mission. It's quite a long journey out to Europa. It's going to take us 6 years to get there. It is the beginning, and it is also the culmination for a lot of people of decades of hard work. This team has been refining the science, developing the technology, building that technology, testing and retesting and testing every part for many, many years. So I'm going to talk a little bit about the product of all that work, why we're going to Europa, and what we're going to do with this awesome mission when we get there. So who am I? Why am I talking to you about Europa Clipper? My name is Ingrid Dauber. I am a research professor at Brown University. And before I was at Brown, I was at the Jet Propulsion Laboratory in Pasadena, California, where the Europa Clipper mission is led in conjunction with APL, the Applied Physics Lab at Johns Hopkins University. There I was part of the Project Science Group, which is a group that helps to organize the science team, interfaces with the engineers, management, and kind of make sure that the science is going to go well when we do finally get there. Here's some pictures of me in the upper left, me with the hardware in the clean room at JPL being assembled. I think this is when they were putting on the high gain antenna, and they dangle the high gain antenna across the clean room, and we're all like, no, and they finally attached it. And then in the upper right, you can see a picture of it all folded up when it was finally all integrated at KSC. These are the solar panels. You'll see some animations later with these enormous solar panels unfolded. And then This is some of the teams that I've worked with, and I'm going to come back to this point again and again in my talk, that this is a very human-driven mission, right? This is a huge team. Over 4,000 people have been part of this mission, and we just launched. So it's huge. This has touched lots of human lives, and it's because of humans that we're going there. On the lower left is the project science group that I'm a part of, and on the lower right is the whole science team, which is about 200 people strong from all over the US and internationally. So let's back up a minute. Where are we going and why are we going there? I probably don't have to explain this to some of you in the room, but just in case, let's all get on the same level. Jupiter, the largest planet in our solar system, the 5th planet out. This is all the planets in our solar system to scale in size, but not distance. It's actually about 5 times as far from the sun as the Earth is. And back in the 1600s, when Galilei looked at Jupiter with his telescope, which probably many of you in this room have done, hopefully with better telescopes than he had. It was not just the resolved disk of the planet that fascinated him, but it was also these 4 dots of light that he saw around Jupiter. And they moved on kind of an hour to daily time scale. And that observation was really the key to the whole Copernican revolution that kind of changed our whole view of where we are in the universe. Things don't all revolve around us. These satellites are actually orbiting another planet, and that was huge at the time. Even though they were just points of light, that really changed everything that we thought about our solar system. Since then, we've been very lucky to visit the Jupiter system with a handful of different missions. Starting with Voyager in the 70s, the Galileo spacecraft spent a long time there around the turn of the century. Most recently, the Juno spacecraft has visited and given us brand new data. And these points of light have really become whole worlds in our view. So no longer are they just a little dot that's moving around, but they're whole globes each with their own unique geology and history. You've probably heard of the closest one in, Io. It's the most volcanically active body in the solar system. I'm going to be talking about Europa, which is the 2nd moon out. Ganymede and Callisto are also really interesting in their own right. These icy, rocky bodies covered with craters that we think are quite old. So what we do know from all these previous visits to Europa is kind of a qualitative understanding of the interior structure of this moon. We know it has a water ice crust on the outside. It's frozen because it's very cold out there. But it also has a liquid ocean of water underneath that ice crust. And below that, it has a rocky mantle and probably a metallic core, much like the Earth. So how do we know there's an ocean when we really haven't visited it? It's covered with this frozen crust. We can't sample down there. The way we can tell, the strongest evidence for this, is from the magnetic field. So Jupiter has this really, really strong magnetic field. It's 20,000 times stronger than the Earth's magnetic field, which we use all the time with the compasses and GPS. And that really strong magnetic field actually induces a separate magnetic field in Europa as Europa passes through the field lines of Jupiter. So the Galileo spacecraft was able to measure the strength and orientation of that magnetic field and see that it was changing with the orbit. And how do you induce a magnetic field in a body like this? There has to be some sort of flowing conductor, some sort of conducting liquid. And the best explanation for something like that is a salty ocean. So we know that there's a salty ocean under there. We don't necessarily know how thick it is, but we know it's there, we know it's global. Now, how do you maintain this much liquid water out at the Jupiter system? It's very cold out there. It's 5 times further away from the sun as the Earth is. It's so cold that the outer shell is completely frozen. There's never any melting of that water ice. But the unique configuration of this system allows this ocean to have formed and to have persisted for billions of years. So on the left, you'll see an animation that's exaggerated. These are both exaggerated. As Europa moves around on a slightly elliptical orbit, it's actually stretched on this tidally locked orbit. so that as it moves closer and further away, that tidal force on it actually changes on a 3.5-day cycle. From the perspective of Europa itself, it's getting constantly squished. Again, this is an exaggeration. It's just a little bit of squishing, but it's enough to cause friction in that rocky interior, and that frictional heating is enough to maintain this ocean over billions of years. So not only is there a lot of water there, we think there's probably even more than there is on the Earth. If you take all of the Earth's oceans and you added them together, the amount of water on Europa is maybe as much as twice that. This is one of the questions we want to answer, exactly how much water is there. But there are a lot of similarities between Earth and Europa that you might not have expected. Europa is much smaller. It's about the size of our own moon, a little bit smaller than that. But it has maybe twice as much water in the form of a liquid saltwater ocean beneath the surface. The structure, we know there's an ice crust at the surface over that liquid ocean in contact with a rocky seafloor, much like on the Earth. And why are we so concerned with water? Well, everywhere that we find water on the Earth, we find life. So this is probably one of the best places in the solar system to look for life other than the Earth. The result of that structure with the icy crust over the liquid water ocean is that it has some really unique geology that we don't see anywhere else in the solar system. So it's got this really fascinating surface. Even though it's very, very smooth at the large scale, there are a lot of variations when you zoom in up close. It's kind of got this like ball of string appearance, you might notice, and that is caused by these long, long ridges, cracks that have parallel ridges on either side, maybe something like a spreading center. These are thousands of kilometers long. They can be straight to slightly curving, and they're overlapping, so we can see generations of these having formed. There are a few craters, even though this is a fairly smooth, fairly young surface, geologically young surface. There are a few impact craters. This is an impact crater named Puil, and it has kicked up fresh material that has not been radiation processed like everything else on the surface. That's what these really bright rays of ejecta are. There are things called lenticulae, which basically just means spots, because we don't really know what they are. Some of them are domed upward, some of them are pits, and some of them actually have compositional differences. If you can see, some of them look darker in this stretched image. So it might be that these involve some sort of liquid water interacting with the surface and transporting materials. There's some areas of terrain that is just all jumbled up and messed up and confused, and so scientists creatively called it chaos terrain. This looks like the pre-existing surface has broken up. These blocks have moved around, they've rotated, they've tilted, and then been frozen back together by this fine-grained matrix. And you can see too, when we stretch these images to get out the color differences, you can see that there are some really interesting materials here. So we think that these might be some of the freshest and youngest surfaces on Europa. This is a specific chaos terrain called Connemara chaos. And you can see these blocks that have been broken apart and tilted. You can see some of these ridges that are pre-existing and some that came after. So we can kind of piece together these geologic histories where we have data that's good enough, which is not too many places yet. This is an artist's conception of one hypothesis for how chaos terrain forms. If there is heat coming from below, it's possible that that icy shell is actually partially molten or maybe just made of like squishy ice. And you could actually get convection within that ice shell, bringing heat up from the bottom that could then melt part of that ice. And you could end up with a kind of a stranded pond of brine beneath the surface. And maybe that kind of pokes through and allows these chaos terrains to form where the blocks break apart and fall in. So this is really interesting because if liquid water is that close to the surface, we really want to see what's in there. This could represent one of the habitable environments that we're really searching for, that we would be excited to find. So this is kind of a cross-section of Europa's crust. with some of the processes we think might be going on. You could have warmer flowing ice, moving heat and materials and nutrients around, and the upper layer cold, stiff ice is occasionally penetrated by either these warm pockets or maybe by cracks that allow material to flow upward, maybe even from the ocean itself to the surface. And this is a really, really exciting, if it's true, it's really exciting to think about this warm, briny ocean water mixing with radiation processed organics that are deposited on the surface, and what that means for the chemistry and the habitability is really exciting. About a decade ago, there was a discovery by the Hubble Space Telescope, and I think the James Webb Space Telescope has more recently seen similar things, indicating that there are ejections of water and maybe other volatiles being spit out of Europa. One possibility for that is that these are actually active plumes, again, of water, either from one of these ponded lakes beneath the surface or maybe from the ocean itself. On the left, you see the actual Hubble data from 2012, I believe, and on the right, you see the artist's conception of what one of these putative plumes might look like. I like to joke that this is kind of like reality and social media, so you kind of want to take it with a grain of salt whenever it says artist conception. But if these plumes are real, this is super exciting. You might have also heard of plumes at Enceladus. We have more data there from the Cassini spacecraft, but they're really interesting. If we were able to use them to actually sample part of the subsurface ocean, that would be a really exciting opportunity. So here's kind of a schematic of all the different kinds of geologic processes we hypothesize might be going on in the crust and interior of Europa and how that affects the surface geology that we can observe. We might have warm ductile ice flowing through this cold outer layer. We might have melt lenses, freezing reservoir. We could have cryolava, where water ice is melted, comes up and erupts, just like rock lava does in the inner solar system. We have these cycloidal cracks that could represent tectonic activity. We have bands and ridges, and of course we have a few impact craters where this material is further mixed together. So why are we so excited about this warm ocean? Let's take a step back. This is a video from Earth. This is not Europa. This is at one of the mid-ocean ridge hydrothermal vents. So these are places in the deep, deep ocean. I think this one is the Marianas Trench, where magma is actually very close to the surface, and that heats up the water there to the point where it creates these black smokers. And before we were able to take videos like this down there, people thought it was impossible for life to survive down there. Well, it turns out it's crawling with life and complex life, right? We see things like clams and shrimp and all kinds of fascinating creatures. So what they're feeding on is they're feeding on the chemical energy. There's no sunlight down there. This is so deep below the Earth's ocean that there's no light energy. So they're feeding on that chemical energy, and they're just thriving down there. So if we have all the same conditions as this on Europa, and there isn't life there, then there's something about life we really don't understand, because we do think that the depths of Europa should look a lot like that. So to summarize all this evidence for why we want to go to Europa, we think it has all the ingredients necessary for life as we know it. It has more water than all of the Earth's oceans combined. It's got these essential elements, both from the original formation of the body and also from impacts. Meteoroids and comets are constantly bombarding Europa, and they're bringing in organics. They're bringing in these essential elements like carbon and nitrogen and oxygen. It also has chemical energy. Even though the sunlight can't reach down into that ocean, it's got hydrothermal, perhaps, systems. It's got radiation bombarding from above, and that chemical energy can set up an imbalance that life can feed off of. And then finally, it's got stability. We think that this system has been existing in a form much like this for 4 billion years. So this soup of really delicious ingredients for life has been just kind of simmering for a really long time. So again, if there's not life there, There's something really fundamental about life that we do not understand. So, in order to investigate this fascinating target, we built the Europa Clipper spacecraft. And I'm going to show you lots of different views of it. Some of the big features that you can see in this view are the solar panels. These are the biggest solar panels ever built for a planetary mission because, again, we're very far away from the sun, not a lot of light, and we need a lot of power to do all this science. We don't have nuclear power. We're fully dependent on solar. You can see there's a magnetic boom. That's one of our instruments that's going to tell us more about that subsurface ocean. And the high-gain antenna is the disk you see on top that's going to send all of this data back to Earth. So I mentioned this is a really big spacecraft. Here are some things for scale. This is the SLS rocket, Statue of Liberty, 6 stacked school buses. I think the previous speaker also has some school buses, so I thought this was apt. The SpaceX Falcon Heavy, enormous rocket, actually the rocket that launched us last October. And there's Europa Clipper once all of the solar panels and all of the instruments are deployed. It's about 100 feet across from tip to tip, about the size of a basketball court, I think probably about the size of this auditorium. So it's just enormous in person. And to give you a sense of kind of the human scale, it's so big that it could not be fully deployed and tested in any existing clean room on the Earth. So these are the solar panels being tested at Kennedy Space Center. Again, they're so big that they couldn't unfold everything at once, so they had to kind of unfold one and then fold it up and unfold the other one. These are humans for scale to give you a sense of that just enormous scale that we're dealing with here. So we also designed the science of the mission. We spent a long time refining this and coming up with what we want to investigate to really get at that possibility of habitable environments on this body. We're going to study the ice shell in the ocean. We're going to answer questions like how thick is that ice shell? How deep is the ocean? What kinds of salts and organic materials are dissolved in that ocean? We're going to look at the composition of the surface. Again, what kind of materials might be coming up from the ocean? What are being deposited from external sources? The geology, I showed you a few of these really fascinating geologic features. We don't really understand how any of those form. We have a lot of ideas for different mechanisms and formation processes, but we really want to understand those better so that we can understand, is the subsurface really in contact with that ocean? How much melt is present? And how much activity is going on today? Are there plumes going on today? If there are, we're going to see them. We might even be able to fly through one and sample it and see what that material is. And then finally, we want to look to the future. We want to do reconnaissance. Hopefully, sometime, we will be able to go back to Europa after this mission and maybe land on the surface, maybe drill or melt down to that ocean or to a melt pocket, take samples and study them in more detail. But in order to do that, we really need to understand what that surface is like. We need to understand, can we land on it? Are we gonna just sink into it? Is it full of like nasty spikes of ice that would make landing on it really, really difficult? We want to understand what kind of lander we would have to build and find the places that are safe and the most conducive for the best science to land. So to do all this, we have a suite of 10 different scientific investigations. The remote sensing instruments are going to study Europa from the UV to the visible. We have an IR spectrometer that's going to do that compositional study that I mentioned. We have a thermal imager called Didymos that's going to look for hot spots and help us understand the thermophysical properties of that icy regolith. We have an ice-penetrating radar called REASON, which will look inside that ice shell as well as give us topography and roughness measurements. And then we have in situ instruments that are actually going to sample materials around Europa. MassSpecs is a mass spectrometer that's going to look at all the materials in the atmosphere around Europa. It's a very thin atmosphere, but there is some material there. SUDA is a dust analyzer that's going to measure the dust particles that are kicked up all the time by micrometeorite bombardment. We have, I mentioned our Europa Clipper magnetometer, which is going to help us understand the nature of that subsurface ocean. And then we have PIMS, which is going to study the plasma environment around Europa. And then we use our radios. We use our high-gain antenna and all the other antennas in concert to study the gravity field around this body to help us understand the interior structure. How big is the core? What is the moment of inertia? And what do we think that interior structure is? This is a video showing you where all of these instruments are mounted on the spacecraft. And the first thing you'll notice is that they're all really close to each other. In fact, all of these remote sensing instruments are co-located, they're co-aligned on purpose so that they can all work in concert with each other. This took a lot of work because there's a lot of complicated technology here, but what we want is we want all the instruments to be able to be pointing toward the same point on the surface, to use data together so that we can combine that data and really get more than the sum of its parts. So I mentioned that really strong magnetic field. This was a real challenge when we were designing the technology of this mission. This is a really punishing environment that it would just fry most electronics after one flyby. So we really can't stay near Europa for too long. And that's the reason we designed this mission. Instead of an orbiter around Europa, it's actually orbiting Jupiter and doing multiple flybys of the moon Europa. So we kind of swing by Europa, and you get this instantaneous radiation dose right when we're doing our closest approach, and then we come back out and kind of recover in the petal of this orbit, send all the data back to Earth, and then do it again every 2 weeks for about 50 flybys. And even though that instantaneous radiation dosage goes away when we go back out very far into the apoapse, the total dosage you can see is continuously increasing with each flyby. So that is just unavoidable radiation damage that we are expecting. You know, they shielded everything they could possibly shield. We have a vault where all the sensitive electronics are behind layers of metal to shield it from radiation. But some of it is just unavoidable. Like the solar panels are going to have some radiation damage after 3 years. And so we just have to design them to still give us enough power at the end of the mission and have a little bit extra at the beginning. So what is this going to look like when we actually do our flybys? Here's Europa passing in front of Jupiter. If we ever get an image like this, it'll be absolutely amazing. Here's our little spacecraft flying over the surface. When we do come in on these closest approaches, some of them are really close to the surface. The closest ones are about 15 miles above the surface, and we're going at about 10,000 miles per hour. Just screaming across the surface with every instrument taking as much data as it possibly can. Before we fly back out and get that back to Earth. So what we do is we have this carefully designed trajectory of all these flybys, and over time we build up a web of coverage around the moon. This is 50, I think it's actually 49 flybys, and it covers every hemisphere, covers the Jovian, the subjovian, and the anti-Jovian hemispheres. We have a lot at the equator, but we also try to get some up at the poles so that we're really getting not just the close-up data when we do these really close flybys, but we're getting regional and global coverage of this moon while still minimizing how much time we're in that really harsh radiation environment. So here's our mission timeline. Our launch date was October of last year. We did a Mars flyby just last month. And then we're going to swing back around and actually do an Earth flyby in December 2026. So you'll probably hear about it on the news. We'll all wave, and we'll see Clipper for the last time, maybe in some telescopes. Maybe you all will see it. And then we finally get to the outer solar system in April of 2030, so about 5 years from now to the date. It takes a really long time to get out there, but I tell myself, you know, other missions have taken a lot longer. Cassini and Galileo and New Horizons have taken, you know, a decade or more to get to the outer solar system. So we have to be a little bit patient, and in the meantime, we find other things to keep ourselves busy. So we did launch. We had a successful launch. Check it off. We did our Mars flyby, and I'm going to show you, and this is, again, an animation of what that looked like. We don't actually have another spacecraft to take this video. And because most of these instruments and subsystems, they were designed to work at Europa, so they're designed to work very cold. Mars is relatively hot, so not all the subsystems are operational during this flyby, but we were able to use it to test both our radar system and our thermal imager. Those data are going to take a while to come down, maybe another month before we actually get to see the data, but the telemetry has told us that so far so good. Everything seemed to work well. The radar system, it's going to be particularly exciting to see those data because it's the first time the whole radar system had a chance to work together in concert. There's all these really long antennas, really long wavelengths. There's just no place that's big enough and also magnetically, electronically clean enough to test this whole subsystem. So this Mars flyby is really the first opportunity to test everything on that radar system. So I want to talk about something a little bit different. This is our vault plate. And this is essentially our version of Voyager's golden record. It's a flat sheet of tantalum metal that has been etched with various things that have in common the element of water and humanity. So we want to memorialize this human touch that humans built this and thought of it and sent it out into the cosmos. And this is kind of our message as to why we're doing this, and also a reminder to ourselves of why we're doing it. On the outer side, which is the upper one here, there are waveforms of over 100 different languages, the word water in each language, and each waveform is a little bit different. And you can go on the website and you can see all the waveforms and also hear the words for water in all these different languages. It's a great multimedia experience. We tried to come up with a visual that represents that sound of human voices. And then on the inside, there's a number of different things. There is a hand-drawn portrait of Ron Greeley, who is one of the kind of founding fathers of planetary geology, a very important person for a lot of people on the team. There's a version of the Drake equation. Some of you might have heard of this. It's an astronomer named Frank Drake came up with this equation trying to quantify the odds of finding intelligent life elsewhere in the universe. And that's actually in his own handwriting, etched on that plate. We have our own message in a bottle where there's a microchip in that bottle that has the names of 2.6 million Earthlings. Maybe some of you in this room, definitely my name, my son's name, a lot of people I know are on there. And those names are etched on there, not just like bits, not ones and zeros, but etched on there in tiny little letters. So those are all going to go to Europa together. There are waveform representations for hydrogen and hydroxyl, which some of you probably have heard of the water hole, where these wavelengths are actually have very little interference, very little noise, and so people have postulated that these might be the wavelengths that are most useful for interstellar communication. And it also, OH and H together make water. So again, we're back to that theme of water. And then finally, there's a poem written by Ada Limon, who is the U.S. Poet Laureate. And we asked her to write a poem about this mission. And it's absolutely beautiful and touching, and it really, I think, helps to kind of put into words some of the feelings that us scientists don't know how to put into words about how beautiful and mysterious the universe is and the mysteries that we want to solve when we get to Europa. So I'm going to play a little animation, and this is the poem read aloud in Ada Limon's own voice.
In Praise of Mystery, a poem for Europa. Arching under the night sky, inky with black expansiveness, we point to the planets we know. We pin quick wishes on stars. From Earth, we read the sky as if it is an unerring book of the universe, expert and evident. Still, there are mysteries below our sky. The whale song, the songbird singing its call in the bough of a wind-shaken tree. We are creatures of constant awe, curious at beauty, at leaf and blossom, at grief and pleasure, sun and shadow. And it is not darkness that unites us, not the cold distance of space, but the offering of water. Each drop of rain, each rivulet, each pulse, each vein. Oh, second moon, we too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves, of small invisible worlds, of a need to call out through the dark.
So I just love that poem. There's also a children's book made of it if people are interested. And so that poem is one of the many ways that we've been reaching out to people, the public, and also amateur enthusiasts like yourselves, to kind of bring everyone along with us on this mission. There are 5 more years till we get there, but we put new stuff on the website all the time, so please do check it out. There's an interactive spacecraft model that I think is really cool. You can like spin it around and see where all the instruments are. There's an augmented reality experience as well as activities for children. And of course we are on social media, and we try to post, appropriate social media things and not just all the fake stuff. So I wanna end with one thought that is unfortunately kind of topical. Europa Clipper is an example of the kind of awe-inspiring innovation and exploration that we can do as humans when many of us work together. But that kind of big endeavor is only possible with public funding. So this is a completely federally funded project. Again, I mentioned it's touched 4,000 people have been employed on this project and helped on it. And that kind of vast and fairly, frankly, kind of risky project, the government is really the only entity that is in a place where it can invest the resources to do this kind of big, life-changing, generational science. So the goal of the Europa Clipper mission, and really the goal of all of science, is to increase knowledge for the benefit of all of humanity, not for profit. So I want to end by thanking the American people and all of you for supporting NASA, for believing in us, for believing in this mission and others like it. And I can't wait to see what we discover at Europa in 2030. Thank you. I think we have plenty of time for questions. Yes?
Aside from the clues that you just mentioned, there's been some controversy in the scientific community in terms of the degree to which the Europa Ocean is isolated from the surface. I was wondering if you'd comment on that.
Yeah, so the question was, I don't know if it's controversy as much as just we don't know how much the ocean is in contact with the surface. That's exactly one of the questions we want to answer. We have evidence that there are some of these geologic landforms look like they have different compositions. How does that happen unless stuff might be coming up from below, right? We have evidence of these possible plumes. That would be very direct communication between the surface and the ocean. But that kind of exchange and understanding those processes are exactly what we want to figure out. Yes?
So what exactly would you look for when you're trying to figure out if it's actually water that's under the surface? Is there specific measurements that you're taking, or specific which instruments on the spacecraft are going to have data that you're going to look at and say, oh yeah, this has got to be water, or oh yeah, there's got to be some light there?
Yeah, so the question was, what are the specific measurements and instruments that are going to help answer questions like, what's the nature of this ocean? Is it really there? And is there life there? I should be clear, this is not a life detection mission. If there's something like really big right on the surface, we'll see it, like if there are elephants down there or something. But I don't think that's what it's going to look like. Really what we're looking for is it habitable? And habitability, the scientists who specialize in this, they've made it clear to me and others that it's not really a yes or no answer too, right? It's not like, is it habitable or not? It's also like, what's the chemistry? Like, how harsh is it? What are the temperatures that, that could exist down there, and what are the materials? So it's this complicated question, and all of the instruments are actually going to contribute to this. Specifically about the ocean, so the gravity experiment is going to tell us about that interior structure, and the magnetic, the ECM, the magnetic instrument, the magnetometer, is going to tell us about the ocean as well. The ice-penetrating radar will be able to detect if there are lenses of melt there within the ice crust. Really, all the instruments together are working to tell us how this whole system works and get at those questions. Mm-hmm. Yes?
On the low passes over in Europa, what is the best resolution you're going to achieve?
Yeah, so the question was on these really low close approach passes, what's the best resolution we're going to get? So the imaging system, I'm a little biased because I worked on the imaging system for a while, but it's a really cool pair of cameras. One is very, very high resolution, up close. It'll get little tiny stamps at the surface. The other one is a wide angle camera that will get global and regional views. Both of them have color and stereo. So we're going to get really comprehensive data. That highest resolution stuff is down to about 1 meter per pixel, and the stereo data will be slightly lower than that, maybe 2 meters per pixel. But that means we'll have 2 meters per pixel topography of this surface, which is just amazing. Yes.
After the Clipper is done with its flybys, what will happen? Will it stop working because of the radiation?
So the question was, after Clipper's done with all these flybys, what will happen to it? And then what was the last part? Will it stop working? Yeah. So I talked about the radiation a lot, right? It's kind of hard to predict that. It's just kind of a stochastic process. Things might stop working. We're always hopeful that we might get an extended mission, but that depends on things like budgets and how much damage there is and what's still working. Eventually, we have a plan to crash it into Ganymede. We don't want to crash it into Europa because even though this spacecraft is really, really clean, it's not clean enough. We don't want to possibly contaminate a site where there might be some form of life. We don't ever want to, get there in a couple generations and say, oh my God, there's life, and not be sure if we brought it there, right? So we don't want to crash it into Europa. We're going to crash it into Ganymede. There's another spacecraft coming from the European Space Agency, JUICE, at the same time, and they have about the same kind of lifespan, so we might be able to coordinate observations with them, and maybe even that end of mission might be coordinated with them. Yes?
What's the purpose of crashing into Ganymede? Doesn't that also have a water underneath the surface too? Ganymede.
What about Ganymede?
You're going to crash a spacecraft into it. Does it have water underneath it as well?
Yes, so the question is, does Ganymede also have water beneath it? And no, we don't think so. We think Ganymede is solid. It's further out, it's colder, it doesn't have as much tidal heating, and we don't see those magnetic signatures that would indicate an ocean.
So by crashing into the moon, are you going to learn something from it?
Well, we might make a really cool crater. This is actually an experiment that we've done on Mars. We've sent hardware to Mars and all these extra pieces. Sadly, some of the missions that didn't work out also made craters, but even the successful missions have things like ballast masses and heat shields, and those make craters. And that's a really interesting cratering experiment in and of itself. Yeah. Sorry, yeah.
Sorry, I'm going to not try to overwhelm you with 3 questions. Okay. Now, you partially answered this already, but I'm going to go into it a little bit. So, first question. As it passes through, hopefully, some of these plumes, to what extent is the first question again, will it be able to sniff out, let's say, the various chemicals? And then 2, is there any way that it'll actually be able to obtain samples and examine them, let's say, microscopic or chemical? And then 3rd, and this is a provocative question, why is there not specific instrumentation in order to determine whether, after traveling 5 times the distance between the Earth and the Sun, they actually found something that's alive? Why would they not have that?
Okay, so let me try to answer all 3 questions in order. The first one was, I think, which instruments and what kind of measurements would we be able to make if we fly through plumes, right? So, yeah, so if there are plumes there and if we can fly through one, we have a suite of all those in situ instruments will be come into play. You know, we have a dust analyzer that's going to look at solid particles, their size distribution, their velocities. There's a mass spectrometer called mass specs that's going to take a sample of that plume material and actually figure out what it's made of. So yeah, we're definitely going to sniff that plume if we can.
Okay.
And then,
is there any kind of microscope to examine it in fine detail, let's say optics?
there's no visual light microscope, no.
Okay, and then the provocative question, why would they not have the instrumentation to go specifically analyze whether there are any processes in any of the material they gather?
Yeah, so the question is why aren't we a life detection mission? Am I getting that right? Yeah. So I think that's a complicated answer. You know, I think yesterday Sarah Seeger talked about even when you have a measurement that seems to indicate life, there's a lot of questions about it. So it's actually a really hard thing to do. One of the ways that we think we might be able to do it eventually is to land on the surface, to dig up material that hasn't been radiation processed, because that radiation is going to kill anything on the surface. So you really got to dig it up. And in order to do that, we have to know what the surface is like first. So this is kind of the first step toward that, but it's something that's really hard to do remotely. And there was a third question?
Well, that was the one. Again, water bears can take a great deal of this kind of radiation and even lack of oxygen and so forth, and literally survive as spacecraft are orbiting the Earth, you know, without all that much shielding.
Yeah.
I mean, I hear you, but I do wonder to what extent this is really more of a political question.
I don't think it's political. I think it's just a hard and expensive thing to do, and we're taking steps towards that as best we can. So, yes.
Do you and your fellow scientists have like a wish list of things that you hope to find in terms of signatures or, you know, specific findings? Or you just open?
Yeah, I mean, ask any scientist, and they have some crazy wish list. Sorry, the question was, do you have a wish list of things you hope to find? And yeah, I mean, a lot of us are really looking for that kind of, yes, this is definitely habitable kind of evidence, like that the chemistry makes sense, that the energy sources are all correct. Me personally, I really like the geology. I love the craters. I would love to find changes in that surface that have occurred since Galileo was there. You know, that's 20, 30 years. We might see like actual active geologic processes that would help us understand what this icy geology is like.
Hi. You know, you're doing these, you're looking at the wrong wavelength. Anyway, why do these flybys where you only have a very short instant, going 10,000 miles an hour? Why don't you try to place the spacecraft in a Lagrange point where it might protect the spacecraft from radiation? You know, because it's hiding behind the moon, and then you can just spend all day there.
Yeah, so the question was why are we doing these multiple flybys instead of being at a Lagrange point, right? And you'll have to ask the trajectory engineers that, but I think the thing is, even if you're at a Lagrange point, you're still bathed in this radiation if you're nearby. It's just really bad everywhere in there. And so what we do is we dip into it and get out as fast as possible. Yeah. Yes.
With Europa's instrumentation, what kind of chemical signatures would Europa be able to detect that might indicate that it was hospitable to life?
So the question was, what kind of chemical signatures might we be able to detect that would indicate it would be hospitable for life, right? So we're going to look at a couple different things. We're going to be able to constrain the salinity and the pH of that ocean. So if we find something that's so saline or so acidic that no form of life that we know of could survive, that kind of helps answer that question. In reality, life on Earth can survive lots of different environments, both radiation and saline and acidic and basic. So there's kind of a range of answers to that, to what might be considered a habitable environment based on that. We're also going to get at the composition on the surface. So we're going to look at the materials that are being deposited there, from bombardment. Io actually spits off a lot of material. Some of that might be landing on Europa, and we'll be able to look at that and figure out where it came from. Yes?
Yeah, I wonder how much does that weigh? And what's the ratio of fuel to weight to get that all the way up there?
So the question was, how much does it weigh and how much of that is fuel? I don't have those numbers offhand, but most of it's fuel when we launch, because it takes a lot of fuel to get there. I can look them up and get to you later, though. All right, well, thank you very much.
Thank you so much. Thank you very much. Thank you.